Next topic is solidification. Solidification is a process by which a substance undergoes phase transformation from liquid state to solid state. This is the usual one where we can see the example of water turns into ice. The pure metals like copper, aluminium, iron, etc. they solidify at a fixed temperature, while the alloys like steel, cast iron, brass, bronze, etc. they solidify at a over range of temperatures. This change from liquid to solid does not occur all at once. They proceed through a series of events. Hence, it is important to study the various changes that occur when the molten metal solidifies. Some of the reasons, a few reasons for need to know about the solidification phenomenon. Uh, they are like one of the earliest and the most widely used application of proper solidification uh, came about when the steel was invented. Iron with just right amount of carbon can make steel, that already we had seen. If the steel, if cooled suitably, takes a ductile form. When it's rapidly cooled, it takes a brittle form. The rate of solidification thus forms a critical factor. Also, during solidification, the material undergoes a phase transformation, like wherein the atoms or the molecules in material are rearranged. Also, in other words, there is a change in microstructure of material. The change in microstructure results in changes in the properties of the material, like strength, toughness, ductility, etc. Hence, the controlling the solidification process, we can control the properties which we can alter as required. Also, the mechanism of solidification of casting and its control for obtaining sound casting is the most important problem for a foundryman. All the metals shrink during change of phase from liquid to solid state. Hence, the proper understanding of solidification mechanism is essential in preventing shrinkage. So, which is a common defect in cast parts. Welding process also involve solidification phenomenon. If you have observed, alloy powders are often atomized and rapidly solidified. This is very important. One of the mode of solidification, as it offers a wealth of information for many practical applications. Let's see the solidification of pure metal. So when a pure metal is allowed to solidify under equilibrium condition, that is a slow cooling condition, the change of state from liquid to solid occurs at a fixed temperature known as a freezing point or a solidification point. If the temperature of metal is recorded at various time intervals during the cooling process, you can see the curve shown in the slide. If you see that figure at point A, the curve represents the pouring temperature, whereas in this point the liquid metal starts giving up its superheat upon cooling. At a particular temperature as indicated by point B, the liquid melt begins to solidify. Like in other words, the liquid crystallizes, crystal starts to grow. And in this condition, there is a two-phase mixtures containing partly liquid and partly solid, which also you can see from the diagram. As the time progresses, the state of point is reached as indicated point C, that is a freezing completed. Liquid is entirely converted to solid. In other words, the crystallization completes at point C. It is a freezing completed stage. So This is A, B, C, this is D. In other words, the crystallization completes at C, as I also told. The solidification begins and completes at a constant temperature because of the evolution of latent heat of fusion by solidifying crystals. So if you see from point C to D, the solid metal cools to reach the room temperature. This is for the pure metal. The same metal, when the pure metal is cooled at a faster rate, there will be a change in the diagram. It experiences considerable difficulty in commencing the solidification. In such case, liquid melt cools slightly below its freezing point. There will be a change. The B will come down. The point B, you will have a dip at that particular point. And actual solidification starts from that point, the dip point. If you name B, the B dash, which is known as undercooling or supercooling. This is about solidification in pure metals. Next, we will see the mechanism of solidification. Mechanism of solidification, in general, the solidification of metals or alloy takes place in the two stages. There is the nucleation, the grain growth. First, we'll see the nucleation. So when a liquid metal cools below its freezing point, it starts to solidify. Atoms tend to freeze, forming very small sized crystals called nuclei. If you see the figure given there, you can see the nuclei named. The moment a crystal begins to grow, we call that as nucleation, and the point where it occurs in nucleation point. These nuclei which have a solidified act as a further crystallization. This is about nucleation. Next is the crystal growth. Second stage. As the cooling continues, more atoms tend to freeze and they may attach themselves to already existing nuclei or form a new nuclei of their own. So each nucleus grows by attraction of atoms from liquid melt whatever is formed. The crystal growth continues in 3 dimension actually. If you see that diagram shown like a stand, it's a 3 dimension. Crystal growth continues in 3 dimension as I told. The atoms attaching themselves in certain preferred direction, usually along the axis of the crystal, and this gives rise to a characteristic like a tree-like appearance. If you see this, it is a tree-like appearance which is called as a dendrite. The dendrites grow in a different direction in each crystal, and finally when one dendrite impinges upon the adjacent growing dendrite, a grain boundary is formed. If you see the second diagram, you can observe that grain boundaries. So each crystal or grain has a different size and orientation. So that will change. Based on that, grain boundaries are formed. However, their atomic structures remain the same. This is about the crystal structure. Those are the crystal growth. So this is how the dendritic structure looks. The three-dimensional tree-like arrangement. Crystal growth. So there is a video which will explain about the dendrite growth. Just observe this, how the dendrites are formed. See again, this is how the dendrites are formed at the edge of the material when solidification takes place. So this is the mechanism of solidification. Next, we will see the effect of non-equilibrium cooling. Like in actual practice, which is extremely difficult to allow solidification, like or cooling, to take place under equilibrium condition. That is, maintaining equilibrium between solid and liquid melt at all times by slow cooling, which results in a non-equilibrium cooling condition, which usually prevail during the solidification of alloys because it is in the range. Slow cooling results in large crystals and also consumes more time, which is not a desirable one, while the fast cooling results in small crystals. This I repeated many times earlier, leading to a better properties. However, if cooling is very fast, then there is a insufficient time for diffusion of atoms to take place, which results in a chemical heterogeneities in the growing crystal, which in turn results in unfavorable properties in alloy. The rate at which the solidification takes place influences the nucleation and grain growth in a material, causing a variation in the size of the crystals formed. Two different phenomena are formed, that is a coring and homogenization with respect to non-equilibrium cooling, and let's discuss that in detail. The first one, that is a coring. Coring or the dendritic segregation happens when a heated metal is allowed to cool rapidly. Rapid cooling causes the exterior portion of the material to harden faster than the interior, that is a core. As such, the core region will have a certain composition, while the surrounding region another composition, thereby resulting in a local compositional difference. So usually the grains in the core region consist of a structure with a higher melting temperature elements. The non-uniform composition produced by non-uniform solidification leads to the anisotropic properties in metals, which is undesirable coring, which is usually usually observed in alloys having too much difference between liquidus and solidus temperatures. It is often being removed by subsequent annealing or hot treatment, hot working process, which is not required in many cases. Next one is the homogenization. Homogenization is a heat treatment process carried out to eliminate coring or a dendritic segregation in a cast structure in order to promote uniformity of chemical composition and microstructure. The alloy is heated slightly below its melting temperature, usually 0.8 to 0.9 percentage of the melting point, that is a TM, and held for a sufficient period of time for a solid state diffusion to take place. It results in a uniform composition throughout the alloy. The duration may vary from 1 hour to several hours, depending on the type of alloy, its structure, and the degree to which the inhomogeneity is liquidated. Homogenization improves the technology plasticity of alloys, technological plasticity of the alloys, and increases the stability of mechanical properties and decreases their directionality in the favorable in one direction. So this is about the effects of non-equilibrium cooling.